Triple integrals. So for regular integrals, integrals of one variable, one would take a width of a small interval, multiply it by height, and get an area of a rectangle, and then make a Riemann sum and sum all of those rectangles to get the area under the graph. We also looked at double integrals, where we took a small area in the region, multiplied it by a height to get the volume of a rectangular prism, and summed those volumes to get the volume under the graph. Well, what about triple integrals? Here we take a volume in space, a small volume in space, and multiply it by a height to get a hypervolume, and sum all of these pieces as a Riemann sum. So what you see here is the region or domain of integration. What you do not see here is the function that's being integrated in the triple integral. If we wanted to represent the function, we would use perhaps something like color, okay, and the spectrum of the rainbow to show the value of the function of three variables at a particular point in space. Nevertheless, what we do here is break up the region of integration into small rectangular prisms, as you see here. And what the triple integral basically is the process of taking the volume of these rectangles, multiplying it by a height or hyperheight, if you will, of the function of three variables, and getting a hypervolume, then summing all of these hypervolumes in a Riemann sum. So we could take a look at this process by increasing the divisions along x. So you see now that our rectangular prisms have a smaller x width, and likewise we could do the same with y and with z. And so we could break up our region of integration into these small rectangular prisms, take each of these rectangular prisms and evaluate the function at a point inside these small rectangular prisms, multiply that hyperheight by the volume of the rectangular prism, and sum all of the hypervolumes to get the total hypervolume under the graph of a function of three variables, which again we would need a w-axis to represent, and so it's not easy to visualize, though colors may be used. As delta goes to 0, we end up getting the region or domain of integration being completely fit by these infinitesimal now rectangular prisms. But just as we did with double integrals, we'll also use the iterated integral approach here. So of course we don't actually take the Riemann sum. We could do a trick with the iterated integral, where now we can say, for example, if the first variable we want to integrate is dz, we integrate z from the surface, okay? Now it's a surface, not a curve, but a surface, gxy to hxy. The next integral then will be a double integral. So we'll also take the iterated integral approach here. So we have the following, okay? If the volume of integration is bounded by surfaces given by functions of xy, okay? So here we had functions of xy, gxy, and hxy. These were surfaces given as functions of xy. They would pass the vertical line test. And if the region of the double integral, so this r, is bounded by functions of x, you could describe it by curves that are functions of x, then the triple integral may be expressed in this manner here. Okay, so again, since the region of integration D may be bound by surfaces that are functions of x and y. And since the double integral is bound by curves that are functions of the variable x, we could then carry out this iterated integral to find the triple integral. Now, of course, one cannot always do that. Sometimes you cannot bound the region of integration with functions of xy. Okay? And also r may not be bound by functions of x. So here, here's in these two cases here, we can bound by surfaces of xy. If we could then bound the double integral that we would take after doing our first integration in the triple integral, then we get what we had up here in the theorem. But if instead we would have to bound the double integral region of integration with curves that are functions of y, then we would integrate over x first and then dy. What if we can't bound our surface by functions of xy? They might fail the vertical line test if you use a line that is perpendicular to the xy plane. What if they would pass the vertical line test if you used lines that were perpendicular to the xz plane? And say the double integral that you would do after you carry out the first integration is bound by curves that are functions of x. Then one would choose this order of integration and have these bounds. And likewise, you could see all of these other scenarios where we change the order of integration. And how you choose your order of integration is, one, convenience. Okay, how much does it simplify the problem? And also, you have to look at how you can bound your region of integration in 3D space. And then after you carry out the first integral, how you can bound the region R of your double integral after that. And just a quick note here that you could see that x up here was bound between a and b. Well, I use the same a and b when discussing an integration along x, but when discussing integration along y as the last integral to take in the iterated integral, I used c and d as bounds for y. And for z, I used e and f as bounds for z for when it's the last integral to take. Of course, please do not confuse that f, which is just a constant that would bound the final variable of integration, with the f that is the actual function. Okay, this is the function. This is just a constant. As you can see here, this is a triple integral being carried out as shown in the theorem. So integrate over z first, and you could see that makes sense since this region of integration d in 3D space d is bound by a top surface, capital H, which is orange there, and a bottom surface, G, capital G, xy, in turquoise there. Okay, so z is indeed bounded between two surfaces, and both of those surfaces are functions of xy. They are not functions of xz. They would fail the vertical line test if you drew a line perpendicular to the xz plane. Okay, then once you carry out that first integral over z, you could see that the region there is best described by functions of x, and so we got the order that we have in the theorem there. Of course, you could always play around with this and change the order, and depending on how your domain looks will determine which order of integration you should use. So if instead, for example, we could bound this as surfaces along the xz plane, then it's a good idea to integrate over y first. So let's take a look at an example. Here we want to find the mass of a solid D bounded by the paraboloids y is equal to some expression of x and z, and likewise y is equal to some expression of x and z. Here notice y is a function of x and z. So this might give us a hint that we should probably integrate over y first, since we could describe this solid as being bounded between two surfaces that are functions of x and z. And this solid has a density given as f equal to 1. Now, when that occurs, when your hyperheight, if you will, is equal to 1, then in fact your hypervolume will be equal to your volume. And I'll have more to say about that in the future, but that's just a little trick to get volumes out of triple integrals rather than hypervolumes. Or to be more precise, when your function of three variables is equal to 1, then the triple integral will give you a hypervolume that is in fact equal to the volume. So how do we find the mass? Well, the mass could be expressed in terms of a triple integral, where here is the density times dv. So you take a small a rectangular prism in your of your solid, multiply it by the density, and what happens when you multiply density by volume? You get a mass, and then you want to add up all of these, the masses of all of these small pieces, these small rectangular prisms that we would fit into our domain to get the total mass. Okay, so we agree that this is what we need to compute, and we'll use a triple integral. The next question is, how are we going to bound our domain of integration? Okay, as mentioned, y is given here as a function of x and z. So the paraboloid is a surface that could be expressed as a function of x and z. So it's a great idea then to integrate along y first. So we're over here in this territory now. So we have our surface given in terms of x and z, and we would like to integrate over y first. We'll deal with the double integral after we carry out the first integral. So here is the domain of integration, or region of integration, for our triple integral. You can see that this region is indeed bounded by surfaces that are functions of x and z, so we'll integrate over y first. After we carry out the first integral over y, we then have to deal with x and z, and we would be left with a double integral r over the 2D region r that you see below there. Also notice that in order to find r, we have to look at where these two surfaces, the turquoise and the orange surfaces, intersect. Okay, and so we should get an intersection that would relate x and z in the x and z plane. Thus, to find r, we'll set these two expressions equal to each other and see where the two surfaces intersect. And solving this equation, we'll get x squared plus z squared equals 1, which means that the region is given by the disk. X squared plus z squared is less than or equal to 1. So here then is a description of the region of integration for our triple integral. We'll have that y will be bounded by these two surfaces. We will then have that z is between the top and bottom part of a circle, and x is between -1 and 1. That does the trick. And so the triple integral may be set up this way. Here's 1. This is the function. It's just equal to 1 up here. We decided to integrate over y first. And we go ahead and carry out that first integral over y and plug in the bounds into the variable that we just integrated. So we'll plug in these bounds and we simplify and get that expression in the inside. Now you might have been taking a look at this and thinking, hey, wait a second, that's circular, and probably it'd be easier to carry out that double integral now in terms of polar coordinates, and you'd be right. We then convert this to polar coordinates, but I should emphasize here that the polar coordinates we're using here is that r squared is equal to x squared plus z squared, okay? Rather than the y squared that we have encountered before with polar coordinates, okay? We could just apply polar coordinates, but in the xz plane instead of the xy plane. So after we convert to polar coordinates, we compute the double integral now, and we get 2 pi as our final answer. Okay, so as a recap, we've noticed that our region of integration D, in 3D, is bounded by functions of x and z, so we decided to integrate over y first. And then when we were done with the first integral, we're left with a double integral that was over a circular region. And so we converted to polar coordinates and found our final answer there.